Hello everybody, and welcome back to Ask Math Anything. This is a show where we answer questions that range across mathematics, but if you've been here before, you've noticed that we usually answer questions that are around algebra or geometry. If this is the first time you've come here, welcome! What we do here is we listen to find out what kind of math questions people are interested in. And this is very different from your usual math class in the sense that it's not something where I'm coming to tell you something that I've already designed. Rather, I've come to go and find out what might you be interested in. And then my goal is to kind of show how all of the math and even science and engineering and everything is all connected. Well, let's go ahead and get started because that's the best way to go and find out what is the style of this live stream here? I see that somebody has commented, don't think it's anyone's first time. Well, actually, I'm not entirely sure about that because every single time we seem to be finding new people. And one of our goals, of course, is to try to reach out to as many people as we can because then it would be neat to be able to bring more people to discuss math. Let's see. Look at that. So we got somebody here, which is the first time. Welcome, Rohan. It's a pleasure to have you. Right. So what's on your mind? Let's see. What kind of questions do we have here? I see. So let's see. Somebody has asked about conic sections. So conic sections, what does it mean? It means that you have to have a cone, right? So if you want to talk about what a conic section is, we need to have a cone. And here's a cone. It looks like an ice cream cone. It also looks kind of like a tornado. But so we've got this cone here. And it turns out that there are a lot of very interesting and natural shapes that you can make by cutting this cone. You see, I said the word interesting and natural because you might say, I could make lots of shapes. Look, I'm going to show you an interesting shape in geometry. Well, it's not that interesting. You see, when I drew something like this, it just looks like a weird blob. And it's very hard to define what is this thing, I don't even know if I could draw this again if I wanted to. So this is an example of a weird shape. But for a very normal, interesting shape, a cone is a very interesting shape. The way you make it is you start with an interesting shape called a circle. And then you just go and you grab another point and you connect everything to it. I'm trying to explain why it's so simple. That it's such a, not so simple, but so natural. And so it's quite interesting to say, what happens if you cut this cone? Well, if I have an ice cream cone, if I cut it horizontally, what's horizontally? Like horizontally, cut it horizontally, then what I would get is I would manage to get a circle. Does that make sense? If you just cut horizontally, you get a circle. What is more interesting is what happens if you cut it at a slant. You know what happens if you cut it at a slant, which is like exactly parallel to this line? If you cut it like this, you get something pretty interesting. If I cut it like this, first of all, it kind of just opens up in that direction. And it turns out to be exactly as Pietro says, it's a parabola. So if I take this and I cut it like this, then I get a shape that turns out to be exactly a parabola. That's why this is a parabola is called a conic section, because you take a cone and you slice it. Ian Ray seems to think that we need two cones. Why do I need two cones? I already got you a circle. I already got you a parabola. What more do you want? Oh, you want an ellipse. Clearly you want an ellipse. The way you make an ellipse is you take this cone and you slice it at an angle. And when you slice it at an angle, you get a shape that looks like this. And it turns out that that's exactly an ellipse. It's like an oval. Now people said you need two cones. Yes, indeed. There's one more shape, which is a conic section shape. And the other shape happens if you try to cut it like this, like cut it vertically. If you cut it vertically, you get something that kind of opens up. But it turns out that it's even more interesting if you have both sides. Why is a hyperbola so complex? Well, honestly, once you see that these are all conic sections, it's not any more complex than any of the other ones. A hyperbola, if you slice it, if you just slice vertically down, you get these two different branches of it. And so this is just briefly explaining these ideas of conic sections. I'm hopefully showing you why these are interesting and natural things to think about, where you might just take two cones and do this slicing. And if you do this slicing, you get a bunch of different shapes. Turns out that all of these shapes are useful. Like somehow ellipses are useful. If some of you know this thing, if you have an ellipse and you stand at one of the points and you whisper, then somehow, there are these elliptical rooms. These are a lot of fun. You can take an ellipse and you can have somebody stand here and somebody stand there. And if you stand at these 2 points and this person just starts whispering at the other person, not at the other person, if they just start whispering, then the sound waves all get to the other person and the other person can hear them, but somehow other people can't hear what's going on because it's just whispering. Furthermore, something interesting about ellipses is that ellipses are the kinds of shapes where if I take this distance, if I add this distance to this distance, and I also add this distance to that distance, they're all the same. An ellipse is something, oh yes, Leo, you're right, they are the foci. Foci means, it's the plural, it's like multiple of focus. And so when I have these 2 foci, there's a really neat thing, which is that this distance is equal to this distance when you include the reflections. And in fact, that's how you draw one. If you want to know how to draw an ellipse, you go and you put 2 pins into the board and you take a string and you just kind of go around it. Okay? Why is this interesting? What's the question? The question was about conic sections, so I'm just kind of saying a few things about these interesting shapes. But here's a fact that I didn't really think about until much later in life, after school. You know, in the ellipse, the fact that this plus this, the purple length, equals the green length, this plus this, is essential for making the whispering work. Because you know like how echoes work? It's like if I go and clap, I'll hear my clap. But if there was a wall and there was some echo, I might hear the clap a little bit later. So the thing is that sound travels slowly. And so given that these 2 points are always the exact same distance apart no matter which route you take, that's why if the person standing here is whispering, it sounds perfect to this person. Or else to the other person, if the path lengths were different, they would be hearing all this garbled junk where it's like echoes on top of echoes on top of echoes. Sort of like, I guess here's an analogy, sort of like how today, if you leave your Zoom call with the microphone and speaker open at the same time, sorry, without the headphones. Has anyone experienced this with your Zoom calls that you have at school, where somebody out there unfortunately left the speaker on and like they didn't plug in their headphones, and then somebody else starts talking, and then you hear, oh yes, OMG, you're right? Then you just hear this like echo, 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 echo. The feedback, it goes nuts. And that's because that's like we humans are not very good at handling sound if it's coming at all these different shifted feedbacks. Look, the fact that in the ellipse, this purple distance equals the green distance is why if this person here is whispering, this person here gets a perfect signal. Like all of the sound waves come at exactly the right time. It's not like one of these horrible like delayed Zoom call feedback reactions. Okay, well that was fun. So this is a little bit about conic sections. Of course, in a real Algebra 2 class, you learn a whole lot more. You learn how to graph these things, you learn like all the equations of them, but hopefully this showed you why they're interesting. More questions. Wuba Song asks, who has really long hair? I do. In fact, I'm really optimistic that I'll get a haircut very soon. As you know, I do these live streams. I also often do interviews for media or whatever. And so I was unfortunately waiting until I finished the last interview in a series. That happened to finish this morning. So my hope is I'll finally be able to get a haircut soon. And don't go to somewhere else to get a haircut. The only safe place to get the haircut is at home or with somebody in your family. I hear that there are some people who are also very good at cutting their own hair. Oh, let me tell you a neat trick that I learned. This is not relevant for me, but I learned this from somebody who had very long hair. And what she said is that she has a really interesting way of cutting her hair. She just takes her hair, which is normally like going on behind your head, and she flips it all forward. So all her hair is like in front. And then she just cuts it across with the scissors. And when she does this, like so she flips all of her long hair forward and cuts it with the scissors. And when she does this, when she flips it back, it's like, it's not a bowl haircut. You know what I mean? Like a bowl haircut looks ridiculous when you just kind of cut straight across here and it's just like this, it looks like a bowl, right? But because she did this, when she pulls it back, it's perfect. Because somehow, like, you know, the lengths of the hair, the hair that goes from the very far back all the way to the front, that one stays longer. And the hairs that are from the front to the down here, those you cut, and like that ends up being shorter. And when you flip back, yes, cool, this is exactly what I thought, right? When you flip it back, it's like, it doesn't look like a bowl. It's like the things that are further back are longer and the things further front are shorter. That is so cool. The first time I heard this, I was like, that's brilliant. And you never have to pay for a haircut. You just kind of do this, and you're done. Unfortunately, it doesn't work for me, because if I tried to do this, I wouldn't even manage to cut the back of my hair. All right. So this was fun. It seems like we have basically entered haircut time, because at this point, everyone has had to stay at home for so long, and even though my state, for example, Pennsylvania, has started to open up again, they've actually said no haircutting place can open up. So everyone's got to figure out how to do haircutting now. Let us talk about math. Yes, let's go talk about math. What other questions can we do here? Okay. Looks like we've got a question from Crazy Vishnu. What is the probability that a person scores 0 marks in a multiple choice question test with 50 questions, each of which has 3 choices? All right. So Crazy Vishnu has an idea. What you're going to do is you're going to randomly guess on a multiple choice question test. Multiple choice question test. There are 50 of them, and 3 choices each. And what you're asking is, what's the probability of scoring 0? Okay, now this thing is something which, we could write down what it is. We'll actually write down what it is, but I'm actually curious how big it is. So we're going to go and we'll write down a fraction, and then we'll go and try to estimate it. All right? So probability of getting 0. Well, you have 50 different questions, right? Oh, you know what? I'll do it for real, and then I'll tell you a joke. But to do it for real, it's like, well, okay, I've got 50 questions, and for each of the questions, for question number 1, there's a 2/3 chance of getting question 1 wrong. So this is question 1 wrong, times 2/3 chance of getting question 2 wrong, and so on. And it goes to 2/3 chance of getting question 50 wrong. So all I have to do is take 2/3 to the power of 50. And how big is 2/3 to the power of 50? If I want to estimate this, what's the easiest way to do so? So I'm just interested, about how big this is. I do know how to estimate powers of 2, but I don't really know how to estimate powers of 3. So maybe what I'm going to do is I'm going to try to I'm going to try to see if there are any convenient things I could do. Leo Yu is right. It's 0, in the sense that it's basically 0. It's very, very small. But I was a little bit curious how small it is. And if I wanted to think about this, 2/3 to the power of 50 to me feels kind of like a big, complicated thing to figure out. Let me just try to figure out a bit at a time. So 2/3 to the 50 is also 2/3 squared, which is 4/9 to the power of 25. Okay, so this is already giving me a way of figuring out how big this is. So 4/9 is already, it's a little bit less than a half, right? Let's say that. So 4/9 is a little bit less than a half. So I can already get an idea of about how big this is. I'll write that this is less than a half. It's not really about a half, but I'll say it's less than a half to the 25th. And powers of 2 are nice to think about, because 2 to the power 10 is 1024. And so that happens to be 1 over 1024 squared, that's 2 to the power 20, times 2 to the power 5 is 32. And so if I was going to estimate this, right, I would say that I already made a mistake going from the 4/9 to the 1/2. And so I'm going to throw away this 1 over 32 and just be in the ballpark. And I'll say it looks like it's about 1 in a million. I'm a little bit curious what the answer is. So I'm now using my approximation to say, it's about 1 in a million. I'm curious. How close is this? Okay, somebody actually did this. I can't count all those zeros. So, you're saying it's 1 in a billion. So in fact, this is way off. That's really interesting. A lot less. So now let's dig in a little bit more. What that's showing is that 4/9, the approximation from 4/9 to 1/2 is too much, in the sense that 1/2 is too big. So since you've brought that up, let's go and try to do this a little bit more carefully. Let's square 4/9. Do I want to square it? I guess I could. Okay, let's square it. So let's square 4/9. That will be 16 over 81 to the power 12 times another 4/9. So now if I look at 16 over 81, and now I can start approximating to something a little bit easier. 16 over 81 is close to 16 over 80. So now I'm going to use this to go up to, it's about 1/5 to the power 12 times 4/9, which is equal to 1 over 25th, 1 over 25 to the power 6 times 4/9. Not really sure where I'm going with this. Not clear that's actually helping much. It looks like I would need to know what is 5 to the power 12 in order to do this properly. So I guess I have to know what 25 to the power 6 is. So that's equal to 25 squared is 1 over 625 to the power 3, and then times 4/9. So we're already getting close. So if I go and see about what this thing is, 625 cubed. 6 cubed is 216. Again, I'm doing lots of approximations. 1 over 216. And then it's 000000 times 4 over 9. And I wrote all of these zeros because I took sort of like 600 cubed. So if I've gotten this, now maybe we're closer to the answer. Because if I say 4/9 is about 1/2, this is about 1 over 500. And how many zeros? 6 zeros. 1 over 500 million. So that now looks like basically 2 over a billion. Was that what you guys had? Yeah, you guys had that. You guys had 1.5 times 10 to the power minus 9. So basically, it's like on the order of 1 in a billion. So that actually shows we're actually a lot better now. This is a lot closer to the answer. The answer is 1.5 times 10 to the minus 9. This is 2 times 10 to the power minus 9. And this is just showing like approximations. But I'm really glad you guys told me the answer, because that showed how you can get so off by just changing 4/9 to 1/2. Is that interesting? I think that's very interesting. This is where a lot of times when people are, when people are doing estimates with multiplying numbers by themselves or by each other, it's very easy to get way off, because you can say, I didn't really change much. However, if you're taking a big power, it makes a huge difference. And that, for example, is why you need to be really careful. Yes, indeed, P14YR0N3 says, doesn't seem like that much of a difference, but it stacks up. And this is relevant if you ever get what's called a credit card. If you get a credit card with something called a credit card interest rate, which looks like a not so big interest rate, it can be very scary because it stacks up like crazy. So, yes. So this is a neat question. That's the probability that you get all of them wrong. It's like 1 in a billion. So that's pretty interesting. If a teacher ever tells you, if you get them all wrong, you get, like I think I once had a teacher who said something like, if you take a true-false test, all right, you have an option. You can also try to shoot the moon. Actually, this was fun. This was a science teacher. He would give these true-false Scantron multiple choice tests, and he would say, you can try to get a good score on this, or if you can answer every single question wrong, I'll give you 100%. Is this a good deal? So now somehow, if you have a 25 question test, he would say, all right, you can either do the test for real, but if anyone ever gets complete 0, I'll give him 100%. Look, it's a terrible deal. If you could get that complete 0, you might as well just answer all the questions correctly. Because it's the same thing, it's a true-false test, right? But his point was somehow, if anyone really manages to be that unlucky to get them all wrong, then, you can get the full score. And this kind of calculation shows with 3 choices for each one, there's a 1 in a billion chance. It's very, very unlikely. All right. I will tell you, if you want, now here's the joke. If you want to, in fact, get them all wrong, there's a much easier way. All you do is on this Scantron, you just fill in all the bubbles. Like all the bubbles. ABC, 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 fill all the bubbles. And then you're guaranteed that it's wrong. Yes, don't do the test at all. All right, but that's not what the question was asking. More questions. What do we have here? Oh, that's interesting. Philip Neller asked, what's the chance of getting 3 correct on this test? How would we do that? Let's try that. Okay, so we've got this test now. There are 50 questions, 3 choices each. I think there was an assumption we were making, which is that you have to answer each question somehow, so you randomly guess. So now Philip Neller is like, what if I want to know what's the chance of getting exactly 3 right? Now we need to do something called combinatorics. Combinatorics will talk about the number of ways I could choose which 3 questions to be right. So now the question is, there are 50 MCQs. MCQ in some parts of the world is used very often to stand for multiple choice questions. In where I grew up in Wisconsin, in America, we never used MCQ, but somehow lots of other places in the world, they call them MCQ. All right? So 50 multiple choice questions, 3 choices. 3 choices each. And what's the probability of exactly 3 correct? Well, for the answer for this, we need to know how many ways could I choose those 3 to be correct. And that requires us to calculate 50 choose 3. That's equal to the number of ways to choose 3 things from 50. And that's equal to, well, there are 50 ways to pick the first one. And after you've picked the first one, there are 49 things left. Let's pick that, 49. And after I've picked the second one, there are 48 things left, 48. But I left some space. It's because, if I'm making a bag of 3 things, the order in which I picked the 3 doesn't matter. So I need to say, suppose I picked, the first one, and the 7th one, and the 9th one. I could also have picked the 9th one, and then the 1st one, and the 7th one. And exactly as temp ID says, divide by the number of ways you could rearrange the 3 things that you've picked. I've got 3 things that I picked, and I could decide in any order to pick them. So that's 50 choose 3. I could calculate this, and I guess let's do it. 6, this is 3, 2 is 6, 6 times 8 is 48. So if I look at the top, I'm just going to approximate now. The 8 times the 50 is 400. 400 times the 50 is 2,000. No, it's not. It's 20,000. Is that right? Now I have to double check. Whenever I do this arithmetic, it's hard. So 3, if I had 8 times 50, it's 400. 400 times 50 is like 20. Yeah, it's like 20,000, okay? So now that's the number of ways that I could choose which 3 I got correct. But once I chose the 3 I got correct, to answer your problem here with the probability, I now need to say the answer is going to be 20,000 times, for those that I decided that I was going to get them correct, there's a 1/3 chance that I really got them correct. And there are 3 of those. And then there's a 2/3 chance that, for each of the other ones, there's a 2/3 chance that I got them wrong. So the way that this works is I go and say, this is how many ways I could pick the 3 times, for those 3 I have to be correct. 1/3 times 1/3 times 1/3. And how 1/3? How it's 1/3 is because there are these 3 questions that I've decided I need to get correct, like number 1, number 7, and number 11. The chance that you get number 1 correct is out of 3 choices, 1 of them. So it's 1/3. And for the number 7, it's also 1/3, and from the number 11, it's 1/3. So that's where this comes from. So I just need to go and multiply this together. And I'm not going to do it this time because we already did an approximation. But if you work this out, you'd find out the answer. Okay, what else can we do? Oh, you know what? I'm going to do this anyway. And here's what I'm going to do. I'm going to do it like this, okay? So I told you I'm not going to do it, but we already have some answer that's going to help me out here, okay? I already know about how big 2/3 to the power 50 is. So let's just turn this into 2/3 to the power 50, right? I'm going to say that this thing is approximately 20,000 divided by 8. 20,000 divided by 8. Oh, hey, there's an 8 over there. I don't like 20,000 anymore. It's not 20,000, it's 50 times 49 times 8. Okay? And now I'm going to take the 8 and throw it into there. Because if I have 1/3 cubed times 8, that's 2/3 cubed. So now I just have 50 times 49, which is about 2,500, times 2/3 to the 50. And I just remember what you told me 2/3 to the 50 was. You told me 2/3 to the 50, 2,500, times 2/3 to the 50 was 1.5 times 10 to the power minus 9. I'm cheating. I actually am using what we just did. All right? So if we multiply this together, the 15 times the 25, that's like 20 times 20, actually minus 25. It should be like 175 or something, I think. hopefully. No. Is that right? 15 times 25, is that 175? Yes, it is. No. That's 375, 375, 375, okay? So this is going to be equal to 3750 times 10 to the power minus 9, which is going to be about, it's about 4 in a million. 4 times 10 to the power minus 6. I think that's the answer. So it's like about 4 over, oh wow, there we go. Caden, thanks very much for confirming. It's pretty close to this answer. And so this is like the chance that you could get 3 of them right. This is some combinatorics, and this is an explanation of how you would use the previous information that you have in order to save yourself a lot of work. As you can tell, I'm lazy. I don't like calculators. And when you guys already did the calculation, that saves me a lot of time. More questions. What do we have here? Wow, it looks like we've got all kinds of different people with the same username. This is pretty intriguing. Oh, Madhav Ramanathan has asked, is engineering more of math or physics? So this is fun because I'm also playing with engineering right now. In fact, what I've spent most of the past few days doing is I've been engineering to make Novid's ultrasonic detection more accurate. And so what am I using? Am I using math or physics? I'm using both at the same time. So in fact, I'm using a lot of math which is related to trigonometry, like sines and cosines, also related to calculus. And so while I'm working on this, engineering to me basically means that there's some interesting principles that you want to use, but the details are really important. You cannot in engineering just say, yeah, in theory you can build a bridge, just go get some metal and like put it together in this shape and it should be okay. Because once you start putting it together, you find out that, oh, when it is 80 degrees outside and I try to stick these two pieces of metal together, something doesn't behave the way it's supposed to. Or like, oh no, it suddenly got really cold and all of my metal poles in the bridge got shorter and the bridge collapsed, right? I'm trying to say that somehow the real world is pretty complicated. And what we're doing right now is we are trying to find out ways to measure distance using just your smartphones. And different smartphones' microphones and speakers are all of different capabilities. So we're using both math and physics. Physics is because you need to understand ultimately why what you're making works. And if you do understand why what you're making should work by the laws of physics, then you can use math to put it together. I think engineering, by the way, is a lot of fun. A lot of people sometimes assume that a mathematician would only like to play with like just math and not actually do anything in the real world. And indeed, there are some people like that. But it's also a lot of fun to go and say, here's a real problem. Here's some real devices you can use to measure things with. And then you try. More questions. Andrew Chow asked, is luck real? Wow. This is a deep philosophical question. How many people believe luck is real? Well, I have a way of answering this that avoids the philosophical questions of like, is everything meant to be or not? My way of explaining this is to say, I'll define two things in my world. One is stuff that happens randomly, and one is stuff that doesn't happen randomly. And that's just the two different categories. How do I know which things behave in which ways? Fortunately, the sun rising every day is in the not happen randomly category. It seems like it always rises, right? And we're lucky enough that it actually always rises on a predictable pattern. And I wouldn't say, wow, I'm so lucky today that the sun rose at the right time. I mean, we're lucky in some sense that we live on this planet, which happens to be close to the sun, yes, and we're able to all live. But we're not necessarily that lucky that, just like the sun rose again today. I mean, it's going to rise again and again and again for like a few billion years still, right? So I would put the sun rising as not luck. But on the other hand, if I'm flipping coins and it's like, oh my gosh, I got 2 heads in a row, I'd say I'm pretty lucky, 2 heads in a row. Now, you know what I'd think if I flipped a coin and I got 50 heads in a row? I wouldn't say it's just luck anymore. I would say something's fishy. Can I take a look at that coin? If you get 50 heads in a row on a coin, that's pretty unlikely, right? And then so you'd say that's probably not a luck issue. Probably there's something going on there that's not random. And then, yes, Leo is right. It could be a special coin. In fact, I used to always carry around a coin in my pocket that had heads on both sides. It's very convenient to have a coin which has heads on both sides for obvious reasons. The only problem, I'll tell you, if you're trying to buy one on Amazon, I couldn't find a heads on both sides coin that really bounced in a convincing way. Because the way people make the heads on both sides coins is that they cut the coin in half. They cut a quarter in half, and then they go and glue the two ends together. And it just doesn't look quite right. Oh, somebody's wondering if I wanted to scam someone. Actually, it was for my math talks. I would often give math talks about probability, and it was very convenient to be able to pull out one of these coins as a prop for one of these math talks. So I wasn't trying to scam anyone. I was just trying to teach math. Right, but I'll then say, like, is luck real? Well, maybe some people have found ways to have strategies in a world which looks otherwise completely random. And in that case, I wouldn't call that luck anymore. I'd call that skill. More questions. Breaking news. Professor Loh uses a special coin to explain math. It was very useful. Because actually I used it for my talk where I was trying to talk about if you flip a coin and you keep getting heads many times in a row, at what point should you start to distrust this person? Aha. Let's see. More questions. This is nice. So Barry has asked, what is your tip on improving math skills for a disciplined non-math student? That's a great question. The key word you said is disciplined. You see, I think that anyone who's disciplined can improve any skills in just about anything. You can even improve skills in sports. If you just decide to be disciplined, you can. Now you're asking, all right, you're disciplined. Now how do you improve the fastest? Use the same thing you use for sports. How do you try to improve yourself in sports? You don't improve in sports by watching somebody else run. How many people improve in sports by watching someone else play soccer? And that's like the only thing you do. You just watch someone else play soccer. Are you going to get much better at soccer? You'll get very good at watching soccer. And you'll probably, there you go. Skylar says by practicing, okay? So you should practice. So now you need to practice. But if all you do is you practice the same kick over and over and over again in soccer, that's also not going to do it for you. There's a reason why in soccer somehow, ideally, if you have a trainer, the trainer starts to say, I think you've got that one down. Why don't you try this other one, which is like a more sophisticated way of running, or try this harder challenge? The key is challenge, right? So the point is, if you want to get better at anything, my strong suggestion is to keep challenging yourself. Don't just try to learn by watching. That's very difficult. Don't just try to learn by doing standard practice. Try to learn by always trying to do something that's just outside of what you know how to do. And if you keep doing that, you will learn more efficiently. And if you're disciplined, you'll be willing to keep doing that. You see, because it's hard if you're not disciplined, because it can be very demoralizing. It's like, well, I don't know how to do this. It's no fun. I'm just stuck. But if you're disciplined, you'll say, this is in fact how I'm going to get better. So I'm going to go and try a little bit harder and try to think your way through it. This is also why my opinion is that if you want to teach someone in this way, it helps to give hints. And so if you happen to come on the weekend live stream, you notice that whatever question I give, for example, if it's a double psych out question, like what we did last Saturday, I'll always give hints. And then through the hints, you'll be able to struggle with it yourself and then take another step forward. All right. More questions. I see that somebody has already been answering to other people about 0 to the power 0. That's convenient because we had talked about 0 to the power 0 in a previous live stream as well. Oh, Ellen Wei is asking about, can you use math to win rock, paper, scissors? And we actually had talked about that earlier in a previous live stream. My general advice is to be very good at generating random numbers, and then you'll at least not lose any more than half the time. What is this? I don't know what this is. So somebody named Jacqueline Zhou has asked, talk about riddles. What is the thing that is as light as a feather, but the strongest animal or human cannot even hold it? I don't know. Let's throw this back out to the audience. What do you think? So Jacqueline Zhou has asked, what is the thing that is light as a feather, but the strongest animal or human cannot even hold it? Air? Oh, that's pretty great. That's pretty good. So I guess I guess it's air. Air or breath. Somebody also has suggested neutrino. Obviously, this person knows a little bit more science. Your breath. This is pretty good. Well said. Okay, I think that we got the answer from the crowd. Jacqueline, is that correct? You're the one who put the riddle out, but people seem to say, your breath. Yes, it is breath. Well, but let's give the credit to all of the audience, because you all figured it out, not me. All more questions. Somebody, Rakshit Singh has said, it is 2 a.m. in India. Love from India, sir. Oh, nice to talk to you from India. It's a real pleasure to be able to interact with people from all over the world. And thanks for staying up late to join us. Oh, okay. So Gabriel Epic has asked, how many vertices does a cube have? So let's talk about this. Let's talk about some other questions around this too. So you asked, how many vertices does a cube have? Vertices are corners. So if I draw a cube, I can sort of see that. Yeah, so a cube here, I can look at it. It's got 8 vertices. I mean, I can see the 4 on the bottom, the 4 on the top. So I have 8 vertices. Now, there's other fun stuff that we can talk about with vertices as well, right? Pietro has said there's something beautiful called Euler's formula. And so that's indeed what I'll mention. And this is something I don't have time to prove because this is a daily live stream. In fact, Euler's formula is proved on one of our online courses. But so if I have 8 vertices, let's talk about other things you might think about when you look at an object like this, like a shape. How many edges does it have? How many edges? What do you see? Skylar Shreya has asked, what was that sound? Well, we do have some people here who are working in the office, working on Novid, and so somehow this is a place that a bunch of different people are using. So how many edges? Are there 12 edges? Well, there are 4 on top, there are 4 on the bottom, and there are 4 going up and down. So 12 edges. And how many faces? Well, you know that. If you roll a die, the number of faces on a die is 6. So 6 faces. All right. So we often will give these some names. We'll say that this is V is 8, E is 12, and F is 6. Okay? Now, let's take another shape. Another shape that I could draw, which is maybe a little bit more complicated. Let's see. Let's draw this shape, okay? So if I want to draw like an Egyptian pyramid. Here's an Egyptian pyramid. How many vertices does it have? How many vertices does it have? So over here, I have 4 on the bottom plus 1 on top, 5. How many edges does it have? The number of edges is 4 coming down from the top plus 4 on the bottom. 4 plus 4 is 8. Okay? How many faces? I have 4 coming down on the sides plus 1 more on the bottom, 5. Okay? So that's another shape. Let me draw one more shape. Another shape that I could draw, let's see. What would be a good shape to use? I'm trying to draw one that's easy to look at and count. But maybe let's go with, well, should we do an octahedron? Octahedron is a bit hard to draw, but we'll draw it anyway. So an octahedron looks like 2 Egyptian pyramids stacked on top of each other. I'm not sure if you can imagine what this is. This is an octahedron. Looks like a diamond, right? And in fact, if you have played some of these board games, you'll have that as a die. So how many vertices are here? How many vertices are here? A 3D diamond. That's a way to think of it. Vertices, there are 4 on this edge, 4 around this way, plus 1 on top, 1 on the bottom, 6. How many edges? There are 4 coming down, 4 going up, and 4 going around. That's 12. Okay? And how many faces? This is an octahedron. That gives away how many faces it has. Octahedron. Octa is 8. So this is in fact an 8-sided die. Okay? So we have 6, 12, and 8. Now, why did I do all of this? It turns out that there is something called Euler's formula. There's a relationship between V, E, and F. Can anyone see what this is? There's something you can always do with V, E, and F, and you put them together and you always get 2. For many shapes, actually for all polyhedra, all of the shapes that are like closed shapes, just like shapes like this 3D shapes, V minus E plus F is always 2. Let's try it. Does it work? Try it for your favorite one of these 3 examples. This is always true. I have 8 minus 12 plus 6. Yeah, 8 plus 6 is 14, minus 12 is 2. 5 minus 8 plus 5. I often like to think of adding first. 5 plus 5 is 10, minus 8 is 2. Ding ding, says Tenpai D. Over here, I have 6 plus 8 is 14, minus 12 is 2. It always works. And in fact, the proof of this is something which is more complicated, but that's in the realm of a proper class. So we won't have time to talk about it here. Yes, so the nice question about the vertices of a cube, now we got to also bring out a neat fact that you can use to look at any 3-dimensional shape. What other questions can we talk about? Is 4-dimensional chess possible? That's a good question. I've never thought about it before. Maybe? 3-dimensional chess already seems kind of difficult. Oh, here's a fun fact. It's like the more dimensions you have, somehow the queen is very powerful in 2 dimensions. But as you get more dimensions, the queen's ability to go and kind of spike out in straight lines is declining. You know what I mean? Like somehow on a normal chessboard, the queen can really go at like all kinds of places. But when you have like a 3-dimensional chessboard, the line that you can go on is becoming more thin. It's only 1-dimensional. On the other hand, if the queen on a normal like 3-dimensional chessboard, if the queen is moving around in like 3 moves, they could actually get to any particular spot. So yeah, multi-dimensional chess sounds interesting. Although I don't even know what the pawns do. Has anyone ever played 3D chess before? I actually have not. It's not clear to me what the pawns do. Like, does the pawn just go in a straight line? And like, is there like a 2-dimensional array of pawns? Is that how it works? Now I'm kind of curious. I wonder if anyone's ever invented 3D chess before. Neat. Okay, some people here have played it before. Sounds like it's a real thing. Let's see. What else can we talk about here? Susan Xu asked, why is the AMC logo an icosahedron? All right, you basically wanted to make me draw an icosahedron, so I guess I'll try to draw an icosahedron. Icosahedron is 20 faces. Yikes! How do you draw a shape that has 20 faces? Well, here's one way. But that's cheating. That doesn't count. I mean, this was just supposed to say I have a shape with 20 faces. No, that's cheating. Here's another way. Okay, I want to show you how to actually draw an icosahedron. You draw first. So here's what I'm going to do. I'm going to draw some things in the back and in the front. Okay, so I'm first going to draw a pentagon. A pentagon, except that some of these edges are in the back, so I'll use a darker color to indicate that they're in the back. All right, so there's a pentagon on top. Now I'm going to draw a pentagon on the bottom. And the pentagon on the bottom will have the 3 of these. Actually, I don't want it to be so far. I'll do it like this. And then I have the 2, I have these 2. Okay, if you ever want to draw an icosahedron, you start by drawing 2 pentagons, one facing up, one facing down. Then you go and take a point on top. And the point on top, you connect to all of these. I drew it slightly offset so I can see that one little connection on the back. Then I take a point on the bottom, and I connect these. And I connect it to the back also. Finally, I make a zigzag like teeth. So I do this. Zigzag. Now I'm going to the back, and since I'm going to the back, I'll change colors. And this is in fact a legit icosahedron. And it looks like this AMC logo. So the way that, not bad, Pietro, the way that I learned how to do this is it's a lot easier if you just start by drawing the 2 pentagons. Once you draw the 2 pentagons, you put the thing on the top and on the bottom, connect, zigzag like shark teeth going all the way around, and boom, it's an icosahedron. And this is the logo on the AMC test. Now you might ask, why is that the logo for the AMC test? I'm not entirely sure. I think that the MAA, Mathematical Association of America, probably wanted a mathematical shape to represent their logo. And why not use the icosahedron? That's one of the most nice shapes that you could find. It's like the most advanced, not the most advanced, it's the most number of faces in any of these Platonic solids, which are these like very, very regular polyhedra. Okay, more questions. Somebody has asked, what is question mark? That's a good question. I don't know. Somebody asked, please can you explain Po-Shen Loh? Hi, I'm Po-Shen Loh. I'm not really sure what more there is to explain. My guess is you probably had another question higher up that I didn't catch. I'm trying to see what might be good questions to hit. We've got 15 minutes left. Oh, interesting. Again, I'm looking through the list that our moderators have found also. Yeah, okay. So I see that there's some questions here which are like some arithmetic type problem. I'll just quickly answer. Willow the Pillow asks, that's a neat name. Willow the Pillow asks, what is 1 minus 2 minus 3 minus 4 all the way to minus 2020? Let's just do this one real quick. So 1 minus 2 minus 3 minus 4 minus all the way to minus 2020. At first, when I looked at this problem, I was wondering if you wanted to alternate the signs between plus and minus, because sometimes that makes like a more sophisticated problem, which is also easier to solve. But this is Willow the Pillow's problem. I see you said yay. So the way I'd think about this is I'd say it's easiest to do this where you think of it as you're adding up all the numbers from one to something else, okay? And in particular, I actually prefer like minus 1, minus 2. So I'm going to do this. I'm going to say it's 2 minus 1 minus 2 minus 3 minus 4 minus all the way to minus 2020. Okay? And really this is the same because the 2 minus 1 is just 1. All right? And now this is another way to look at it. It's 2 minus the sum of the numbers from 1 to 2020. 1 plus 2 plus 2020. I like to use the sum from 1 to 2020 because I do that a lot, and that will help me not make a mistake. The way to do this is you say, if I'm adding up a sequence of numbers from 1 until something, it's just how many numbers there are times the average value of the numbers. How many numbers are there from 1, 2, up to 2020? Well, we're counting. 1, 2, 3, 4. There are 20 of them. So there are 20 of the numbers, and the average of the numbers is the same as the average of the first one and the last one. Right? Because they're all equally spaced. So the average of all of these is just the average of 1 and 2020, which is 2020 plus 1, 2021, divided by 2. And now if I wanted to solve this thing, I guess, I just have to actually do some calculation. What happens here? This is 2 minus 1010 times 2021. This one I'm willing to do. The reason I'm willing to do this is because multiplying by 1010 is fun. 2021 times 1010, when you multiply, I get okay, let's ignore the O. And then I guess I should ignore the O, and I get the 2021. I'm already going to go straight to this one. It's the 2021 from there. I'm going to do this multiplication in a way that you're probably not used to. I'm going to put the 1 over here, so the next one is an O. All right, and then wait, something terrible happened. Is that true? I think this is okay. And then, oh yes, that's right. The O would be over here. Okay, let's just not confuse people, okay? I'll say there's a 0, and then there's a 2021 over here. Then there's another 0, and there's a 2021 over here. And when you add this together, what you find out is you're just shifting the 2021, and that's why it's fun to multiply by 1010. You just shift the 2021 and then add them together. So if I add them, it looks like it's 20412110. All right? And now that happens to be this piece. I take 2 minus that. And when I take 2 minus that, it's a negative number now. And I'll get 2041208. I think that's my answer. I'm not sure if this is right, though. Let's ask people. Is this right, or did I get this wrong? It could very well be that I did my last subtraction wrong. But looks like it's okay. It looks like it's okay. So this is the answer. And the reason I was willing to do the calculation for you is because I just wanted to show you multiplying by some number which has a lot of zeros and ones is really fun. You basically just kind of make a copy, shift it over, and just like add straight down. And it's not as painful as if I had to multiply 2021 by like some 3974 or something terrible like that. All right, more questions. Colin Z asked, where did you learn how to draw an icosahedron? Well, I just tried to figure it out. I mean, I think I was curious about these kinds of solids, and at some point I thought to myself, how might I try to draw the icosahedron in a way that would be reasonable? And I came up with that. So it's just like when you go and think about things from scratch, you might be able to come up with good ideas. James Jin, what's the best way to memorize something? It's to understand why it's true. It's to not really memorize something. Like here, you just saw me do the sum of the numbers 1 plus 2 plus 3 up to n. Many people remember it, that's n times n plus 1 over 2. That's dangerous. If you ever forgot whether it's n times n plus 1 or n times n minus 1, you're stuck. The way I remember it is, look, I'm adding up a bunch of numbers. So the sum is how many times the average. Of course, that's actually what the average means. But then over here, I can just go and say how many? Oh, obviously, 2020. What's the average? It's the average of the first and the last. So I'm done. So I recommend that the way you memorize something is to go and think about, about what might be the reason why it's true. Madhav Ramanathan has asked, why is geometry not interesting or so interesting? I'm not sure which one you said because it zoomed away, but I'm going to say geometry is actually really interesting. The reason it's really interesting is because it's sort of the study of all these neat coincidences you can get when you draw such simple things as lines and circles. Depending on how you're learning it at school, from whatever textbook you're using, it could potentially in the textbook seem like it's routine. However, it's actually a subject that fascinated people for thousands of years because everyone was wondering, what can you do with these? What can you do with these perfect circles? And it's neat when you find out that I just start with circles and lines and a whole world emerges. Cadence Xia also says it helps your brain. I'm not sure if that was a response to the geometry, but it definitely is true about geometry. In fact, when I was doing math contests in high school, geometry was the subject I spent the most amount of time on. And when I spent all this time on geometry, I ultimately learned how to think. And nowadays, I do very little of just that same kind of geometry, but I use all the thinking methods for everything else I do. Oh. Susan Xu, if you didn't do math, what would you major in? I almost majored in computer science instead. When I went to college, I was in fact planning to do computer science. It's important to know that for many, many years, when I was in middle school and high school, I spent a lot of my time writing computer programs, which is actually the reason why today, when I thought of the Novid idea, I dared to start it. And in fact, even today, I'm one of the people who's writing the code that makes the core parts in the middle work to give the technology that senses distance. But I was spending so much time on computer science that I was originally planning to go to college and study computer science. It just so happened that the university that I went to, Caltech, at the time I went there, didn't have computer science as a major. It was actually not possible to major in computer science at Caltech when I went there in the year 2000. So I guess I didn't major in computer science, right? I then decided to go and major in mathematics instead. But even before deciding for sure to do math, I had spent a lot of time learning physics. So I even considered majoring in physics. It's worth mentioning that, about 20 years ago, not everyone in the world was saying, I'll go to college and I'll do computer science. Computer science is a relatively new thing. On the other hand, about 20 years ago, the people who went to college with a lot of math background, who wanted to go and do something real world, would usually study physics It's actually quite interesting that it used to be that from math you went to physics. Nowadays, from math, most people go to computer science. But for me, I really love the physics. And to this day, I think that physics background has been very useful to me. Hi, Jacqueline. So, okay, what else can we do here? Bear Z asks, what's the point of radicals? Radicals, do you mean things that look like this? Well, the point of radicals is because there's something you're trying to do in the world that needs the radical. And so, can anyone think of anything in the world where you might ever need to do the square root of 4? It happens quite a lot. There are a lot of things in the world where I need to know what the square root of 4 is. For example, if I drew a square, and if I told you that this square has an area of 4, then you find yourself having to find the square root of 4. And so this is an example. Oh, right triangle is another great example. If I drew a right triangle, and I have 3 and 4, then the Pythagorean theorem tells me I need to write down the square root of 3 squared plus 4 squared, which is the square root of 25. And so it's telling you that you need to, oh yes, okay, you guys like me to write 5. It's 5. So you need to go and take the square root to do something. And whenever we invent notation in mathematics, it's because it's a commonly done thing. And so radicals are really useful. They give us the ability to do anything that we need to find the square root of, which is quite often. There's another reason that radicals come up. It's in the quadratic equations. If you have any old equation of the form like x squared, whoa, these are weird 2's. X squared plus 3x plus 5 equals 0. If I draw anything like this, I will need the square root to express what the answer is for x. And so that's why the radical is very, very useful. Oh, wow, no name. Thank you very much for bringing up this alert. It's very important for me to mention, tomorrow's live stream starts 1 hour early. So we will be doing the live stream from 3 o'clock to 4 o'clock Eastern time instead of 4 o'clock to 5 o'clock. The reason is because I'm also working on Novid, and we have a meeting that came up which happens to be during the normal live stream time. But I'm still going to do the live stream, so I'll see you guys at 1 hour earlier than usual tomorrow. For those of you who were staying up late on the other side of the world, this makes it a little bit easier. You only have to stay up, well, 1 hour less. Let's see. What other questions can we do here? I'm looking at all of these things. Bear Z was just making a joke. What's the point of decimals? It's so that we can express these numbers in a more efficient way. In fact, decimals are a really, really good invention. A long time ago, people just used Roman numerals. What in the world would you do for decimals? Okay, so I see that there's a question that somebody was asking, and this might be a one to end with. Oh yes, let's end with this one. Andrew Chow, do you like art? And I'll say yes, I like art. I like art in the sense that to me there's lots of different kinds of art. Some kinds of art are visual, some kinds of art are with words, some kinds of art are with sound. To me, art is somehow finding something beautiful. In fact, you can even have art through math. To me, art is just finding a beautiful way to do something. Oh yes, you can even have art in sports. Some people say, oh my gosh, what a beautiful shot, right? So to me, I have a certain thing about beautiful. Beautiful is somehow when you've gone beyond what expectations might have been. And if I was trying to say like what this means mathematically, there's somehow a lot of normal stuff that's going on in the world, and occasionally something rises above, like a 4-leaf clover. That's another example, right? And now those are all just like natural anomalies. Oh, that was such an oxymoron. But I just mean like those are like things in nature that are unusual. Art generally is something that's made by humans. And so I think it's really interesting whenever somebody finds an interesting way to evoke an emotion, whether they did it through written word or through music or through what they had happened to draw. And I just appreciate that. I think it's just beautiful to see what people are capable of doing. And that's what makes us special in some sense. That's why people are special. Because if not for that, we would just all be a whole bunch of robots. And that would be really boring. Right. So that would be my answer. And if you're ever wondering about like, should you do art or should you do math or should you do any of these other things, my feeling is that they all can come together. And people who have an appreciation for art might even be pretty good at coming up with interesting mathematical theorems or interesting mathematical approaches, because you are looking for that beauty. Okay, well, unfortunately, it looks like we have reached 5 o'clock, and so this particular live stream for today, since we in fact managed to start on time, we will in fact also end on time. But I want to thank everyone who came today. Hopefully, if you were new, you got an interesting experience, which is maybe not what you were expecting. But hopefully you found this to be a way that you could see answers to random questions that are very natural, that come to people's minds. I'll be back tomorrow, 1 hour earlier than usual. See you there.